All right, let's start. Good morning.
Morning.
So, how was the midterm? Good, bad? Yeah. Yeah, we'll see. I haven't started grading, but by the end of this week, you'll receive your grades. I grade rather leniently, and I don't really, I don't like punishing due to calculation errors, but we'll see. There has to be some sort of a, distinction between different performances after all. But yeah, so this week we're going to transition to determinants. So this week is all about really computing determinants. We had already learned how to compute determinants of 2 by 2s, namely AD minus BC. But we want to really understand what that number is, what its significance is from a perhaps geometric point of view. And then we're going to learn how to compute determinants of larger matrices. But ultimately, just like in the 2 by 2 case, determinant is going to be a number that you can associate to any square matrix that, when non-zero, tells you that the matrix is invertible, just like in the 2 by 2 case. I really like sort of thinking of 2 by 2s and understanding the situation in the 2 by 2 case, and then I sort of generalize it in my head. Things get more complicated. For instance, how to compute the determinant of a 3 by 3. It's more complicated than AD minus BC, but once you get the main idea, it becomes somewhat more manageable as far as I'm concerned. Two things, or maybe three things that we need to discuss from the previous weeks that I kept pushing around is this block matrix algebra business, which in the problem set due this Friday, there's a problem about. Somewhat of a more abstract problem, in fact. Has all letters and stuff. I also want to talk about these affine stuff, affine subspaces of vector spaces and affine transformations. So these are almost like linear subspaces and linear transformations, but they're slightly more complicated in a sense. And then tomorrow, probably, we're going to talk about LU type factorizations and elementary matrices. So these are today, tomorrow, elementary, matrices, and LU type factorizations, decompositions or factorizations. Okay. Now, first, let's get this block matrix stuff out of the way. I'll start with an example. Okay. Another name for these block matrices is partitioned matrices. Probably it's better to write it here, actually. So here's an example from the textbook. Okay, let's remind ourselves this matrix multiplication as well, because ultimately it's not that deep, this block matrix multiplication business or block matrix algebra. Okay, sort of like an extra thing. So let's say that A is 2 minus 3 1 0 4 1 5 minus 2 3 minus 1 0 minus 4 minus 2 7 minus 1. That's A. It's a 3 by 5. And let's say B is this 5 by 2. Six minus 2 minus 3 minus 1 5 4 1 7 3 2. Okay. So let's remind ourselves, whenever we see a matrix, we put the number of rows here on the bottom left, and here we put the number of columns, And likewise here, this is 5 by 2. This tells me that because the number of columns of A matches with the number of rows of B, I get to do this multiplication A times B, but not necessarily B times A. Okay? And when I do A times B, I'm going to get a 3 by 2. Then let's write it. Maybe like this. Right, so the middle dimension is 5. You cancel that out, and you end up with a 3 by 2. Is well defined, let's say. Is well defined. Is defined. Okay. Let's compute this. This is just a review in a sense. In a second, I'm going to connect it to block matrix stuff. I'm just going to write down these things side by side. That's A, and then B is this guy. Remember, whenever you see two matrices side by side, when you're trying to multiply them, the left matrix you turn into a bunch of rows, and the right matrix you turn into a bunch of columns. And then you're going to mix and match. Then first row, or rather first column, second column. I'm going to end up with a 3 by 2. Let's do this slowly, like this. Okay, I allocated my memory. Well, I might as well try doing this by in my head. So 12. Okay, I don't trust myself today. Let's write it. This, and then minus 3, and then plus 0, plus 20. Right? I just multiplied the corresponding entries like this. And I'm just adding all of them up. Whatever that end result is, that's the 1 entry of the product. Then I keep going. For this entry, I need to look at the first row, and I need to hit it against that second column. So this is now 8 minus 3 plus 7 plus 0 plus 8. This, now I need to take the second row and hit it against the first column. So 6 minus 10 plus 6 minus 3 minus 5. This against this is 4 plus 5 minus 14 plus 9 minus 2. This one, 0 plus 8 plus 6 minus 7 minus 5. And then this one finally is 0 minus 4 minus 14 plus 21 minus 2. Okay, let's consolidate everything and keep the shape. So what is this? This is 3, 15, 35, 16, 20. Okay, 12, 2, minus 1, minus 6. Minus 10, minus 12, minus 3 plus 2, I think. Okay, and then let's try to combine. This gives me 1, this gives me 1, that's 2. 18, 21. Does this match? Okay. Okay. So you can do it this way. This is the standard matrix-matrix multiplication. Let's record it on the side. first row is wrong, according to the textbook. Made a mistake somewhere. So 12, 18, 15. Oh, because I used there's a -4 in the textbook. Okay, then I guess probably it is correct then. Let's not change this. 2, 2, 1. This is what we found. Now, the idea of block matrix multiplication is, well, you can just do pretty much all of these things, but instead of thinking of scalars as scalars, you can replace your scalars with matrices insofar as matrix multiplication works. Meaning, for instance, instead of thinking of this A as a 3 by 5, you can think of it as a 2 by 2 with some of the entries matrices. Okay? I'll delete this. So I want to think of this as a 2 by 2. In the textbook, for instance, they split the rows into 2, 1. So instead of 3, I'm going to write 2, 1, meaning I'm partitioning like so the rows. First 2 rows and then a 1 row, single row, and then 3, 2. Okay, so 3 columns, partition like this. And then just like with the standard matrix multiplication, in order for this partitioning to work, you need to, if you're partitioning the columns of the left matrix like this, you need to partition the rows of the right matrix in an appropriate fashion. So you need to split it into 3, 2, meaning 3 rows, then 2 rows. And then I guess we'll just keep the 2 here, meaning I'm not splitting the columns of B. And so you get to write it like this. A equals A11, A12, A21, A22. Here, for instance, A11 corresponds to this 2 by 3, and so on. And you get to write B equals B11, B21. And again, this B11 corresponds to this, B21 corresponds to this 2 by 2. And somehow, if you sort of store your scalars, combine them and then store them into these matrices, you can still pretend that these are scalars and do matrix multiplication, and it's going to give you the same thing somehow. Okay? So what you say is this. Then AB is, well, like this. Now you say, okay, even though these are not necessarily scalars, I'm still going to pretend that I have 2 rows. I'm saying, oh, this is a 2 by 2 against a 2 by 1 with matrix entries. That's what you say. Splitting the rows and columns in a compatible fashion like this essentially allows you to do what I'm going to do in a second. So you split the left matrix into rows, block rows if you want, right matrix into block columns, and then you multiply as if these are scalars. Okay, so 2 by 2 times 2 by 1 is going to give me a 2 by 1. Here it's going to be A11, B11 plus A12, B11, B21, sorry. And then here I'm going to have A21, B11 plus A22, B21. Okay. Let's see that these indeed make sense. So now you see all of these are supposed to be matrix-matrix multiplication and then matrix-matrix addition and so on. So for instance here, A is 2 by 3, or rather A11 is a 2 by 3. I'll write it here. And B11 is a 3 by 2. So when I do this multiplication, A11 times B11 is going to be a 2 by 2. Does that make sense? Then I look at this, A12, what is that? It's this entry, meaning it's a 2 by 2. And B21 is a 2 by 2 also, which means that both this and this is a 2 by 2. And so they are vectors of the same type, which means that ultimately I'm able to add these. So the first row makes perfect sense, and it's going to give me a 2 by 2 at the end. That's the idea. Same thing with this. A21 is a 1 by 3. B11 is a 3 by 2. So this product is going to be a 1 by 2. A22 is 2 by 1, or rather 1 by 2. B21 is 2 by 2. So you see, even though the middle dimensions are not the same, when I do this matrix-matrix multiplication, I'm going to end up with a 1 by 2, and here too I'm going to end up with a 1 by 2, so that the second row is going to be a 1 by 2 in and of itself. So maybe you can sort of separate it like this. This and then 1 by 2. Let's do just one of them. Let's compute the first one. So ultimately, that result should match with this. It's just that it is partitioned. Your data is partitioned into sort of two sections. So for instance, A11 times B11 plus A12 times B21 is this. I'll use blue, in fact. A11 times B11, 417, plus A12 is this, 2 by 2. B21 is this, 2 by 2. Oh, that's a 2. And so I'm going to end up with a 2 by 2 ultimately. So let's do this first multiplication. Okay. 12 plus 6 minus 3, 15. 8 minus 3 is 5, plus 7, 12. 6 minus 10 plus 6 is 2, exactly. 4 plus 5 is 9, minus 14 is minus 5. Okay, so that's the first part. Then we do this 2 by 2 multiplication. So this is nice. That just gives me 20 here, and then 8 there. And then this by this is minus 3, minus 8. 9 minus 2 is 7, and then you add everything up. 35, 20, minus 6, 2. Okay, you see, this computation did really give me the corresponding parts in the product. And you can do the same thing with the second row. I'm not going to do that. I'll leave that to you, in fact. This part for you. Now, what is the benefit of this? Well, there's multiple benefits. Because, so the way I think about it is that, this A matrix is supposed to be going from R5 to R3. It's one transformation. But typically, when you have a transformation like this, it comes from sort of different components. So you don't, in certain situations, maybe you don't want to go all the way into the indices by themselves, but you want to sort of combine certain subparts of your data, of your transformation. Trying to think of an example. Yeah, so for instance, imagine this A to be the sort of lighting system in this room, right? It has lots of components and so on, and if something goes wrong, you may want to sort of try to fix a certain part. Maybe you want to sort of fix a cable, or maybe you want to fix one of these buttons or something. Once you sort of troubleshoot, you figure out where the problem is and so on. But depending on what you're actually trying to solve, you almost never go all the way up to the sort of atomic level. So you're not really going to be worried about the transistors and stuff like that. If something is wrong with the transistor in one of these sort of circuits, or in one of these small machines, you're not going to try to fix that specific transistor. You're going to try to replace the machine itself. So we would like to be able to look into certain components of transformations, but sometimes maybe not all the way until we see sort of nothingness and the quarks and stuff like that. Okay? So that's why it ends up being useful to sometimes use block matrices. Yeah, I mean, initially when I first learned this stuff, I didn't really see the point, but this block matrix stuff shows up quite often. Because somehow it's like, one of the things you end up doing is, well, you have one complicated system and then another complicated system, and then you put them together to get a more complicated system and so on. Yeah, go ahead.
How do you determine the partitions? Like
it doesn't matter, actually.
So if I pick like any arbitrary partitions of that matrix,
yes,
I would still get the same result.
Yes, yes.
Okay.
Yeah, it's all in your head. You can do this if you want. You can do this, okay? Now this is a 1, 2 times, so 1, 2 by 2, 3. In fact, let's do this. 2 separation, 2, 2, 3. 2 to 1. You would need to split this in the same way as well. So like this, and then let's split it like this if you want. And think of B as 2 to 1 by 1, which isn't really that much of a splitting in this case. But if you were to partition your data this way and do matrix-matrix multiplication using block matrices with this splitting, it's still going to give you the same thing. Yeah. Yeah.
Can you explain why you split it the way you did?
I mean, this is an abstract example. It really doesn't matter how I split it. Like the first splitting was because it was the example. There are certain situations where, it becomes more apparent in applications. Let's put it that way. Yeah, think of it like this, perhaps. I mean, it has to be more applied in this context, but let's say you have a simple linear model about sort of like a prey-predator system. So you have two populations, let's say owls and rats, and your time is discrete, like in the Fibonacci rabbits situation. So owls themselves have a certain sort of life cycle. They're juvenile owls, and then they turn into adults, and then eventually they die. So that's one system. There's one system, which is one matrix for owls, one matrix, likewise, for rats. But then you want to talk about the whole system. So there should be like a larger matrix that incorporates both the owl matrix and the rat matrix. Okay? It should say, oh, the more there are owls, the less rats should be able to survive, or something like that. That's what you encode. And so in that case, you would sort of partition your large system matrix of that incorporates this prey-predator system into parts about, oh, this is the part coming from the owls, this is the part coming from the rats, and so on. You will sort of analyze that, and then you would say perhaps, oh, now I'm going to introduce one more thing, in fact. I'm going to introduce worms too. I'm going to make my system more complicated. Yeah. Does that kind of make sense? Yeah. Like in abstract, it's not really that clear why you would partition matrices this way. But yeah, so in applications, it becomes more meaningful. The only thing that matters is that, you see, you get to split your matrix like this into smaller matrices, and you get to pretend that these are scalars pretty much. That's how I think about it. As long as the partitioning of this matches with the partitioning of this, so that you can do this standard matrix multiplication thing as usual. Okay. It's really not that deep. But it's very convenient. It's more convenient than it looks. Any other comments or questions about this? Okay, let's now transition to affine subspaces. Oh, here's, for instance, one nice example. I'll give it as an exercise. So, well, I can think about diagonal matrices first. Let's say A1, A2, dot, 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 AN, and zeros otherwise. Okay. One of the nice things, so we've seen diagonal matrices often. Why these are important is because, well, they keep axes and so on. Another thing is that it's very easy to compute the inverses of diagonal matrices. Namely, the inverse of this diagonal matrix is again going to be diagonal. And it's going to be the diagonal matrix where the entries are the reciprocals of these numbers. Okay? So 1 over A1, 1 over A2, and so on. You can do row reduction too, of course, or you can just multiply these two to realize when you multiply this with this, you're going to get identity matrix. Well, if you had a block diagonal matrix, you have the same formula, for instance. As an exercise, let's say your matrix is A1, A2, dot, 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 AN, and all 0 blocks otherwise. You have a block diagonal matrix. The inverse of this is going to be the block diagonal matrix with diagonals the inverses. Pretty nice. You get to compute like inverses of things very fast. So for instance, a nice example of this is something like this, perhaps. I'll erase this. I'll take a shear and put a bunch of shears on the diagonal. 2 by 2 shears. So for instance, say A is this 2 by 2. That's a shear matrix. Its inverse is 1, 1 on the diagonal, minus 1 in the off diagonal. Because this shears one way, and to revert it, you need to shear the other way around. Okay, that's the inverse. So if I were to look at, for instance, this, and then all zeros, which is nothing but this, of course. The inverse of this, you see, is, well, it's going to be the block diagonal with this on the diagonal. So helps you sort of fast forward a bunch of calculations like this. you can, like you don't have to use block matrices and you don't have to be comfortable with this, but you see, I look at this for instance, and in my mind I partition. I look at it and I say, oh, can I sort of partition this so that I have things that are non-zero only on the diagonal? And then this is the partitioning I see in my mind. Sort of collapse, like instead of this 2 by 2 0, just have a large 2 by 2 0 matrix and just invert that. Like I said, you don't have to do this. You can just go ahead with row reduction and so on. But this is a 6 by 6, you see. And it has a bunch of zeros too. So makes things very convenient to just like compress, abstract out, black box, whatever. Okay. So the last problem in this problem set is about coming up with one of these sort of shortcuts. I don't think so. I think instead of asking for the inverse of a diagonal, I think I'm asking for the inverse of a general block matrix with 2 by 2s. But the idea is the same. Okay. Any other comments or questions about this? Okay. Now here's a definition: affine subspace. Affine subspace is pretty much the same thing as a linear space or linear subspace, but it doesn't need to go through the zero vector. So if I were to, for instance, on the plane, look at lines passing through the origin, these would be one-dimensional linear subspaces. But if I were to look at an arbitrary line that possibly doesn't pass through the origin, that would be an affine subspace. So, example, my spaces are 2, for instance. And this line would be a linear subspace. Any linear subspace is also an affine subspace, but not vice versa. So this is y equals x is both a linear subspace and an affine subspace. So both a subspace or linear subspace but if I were to look at y equals x plus 1, then it doesn't pass through the origin. And then, even though it is still a line, but it's not technically a linear subspace. It's an affine subspace. So y equals x plus 1, when x is 0, passes through 1, so it should be like this. Same slope, right? This is an affine subspace, but not a linear subspace. Affine subspace, but not a linear subspace. Nope. What is the definition? The definition is, well, an affine subspace of a vector space is, well, it's a translation of a vector subspace or linear subspace. So how did I get this red line? I started with the subspace and I moved it. That's the general definition, essentially. So let B be a vector space, an affine subspace of V is is a set of the form span of S plus V0, let's say. So you take a set of vectors, you look at the span, so now you have a subspace, and then you translate it using some vector. Okay. For some set S of vectors, in B and some V0 in V. If you're familiar with differential equations, somehow linear subspaces correspond to ODEs with no forcing, no force function, and affine subspaces correspond to ODEs with forcing function. If that doesn't make any sense, don't worry about it. So for instance, I can, in this case, what I can say is y equals x is the span of E1 plus E2 blue. This is the span of E1 plus E2, E1, E2 being the standard vectors, 1, 0, and 0, 1. And this is a diagonal line. But then this would be span of E1 plus E2 plus E2. Take the span so that you have a subspace, and then you move it around. Take this line, move it up by 1 unit, and you get the red line. That's what I mean when I write this. Okay. A nice exercise is that in general, affine subspaces are not closed under vector addition. They're not closed under linear combinations, but they are closed under linear interpolation. That's a nice property. I'll write it here. Exercise. In general, affine subspaces are not closed under linear combinations. Right, so for instance, well, E2 is in the red line, but twice E2 is not, for instance. But they are closed under linear interpolation. Meaning, if you were to take any two vectors in the same affine subspace, then any linear interpolation of these two also going to be in the same affine subspace. But they are closed under lerp. Meaning, if I take, so what does this mean? This means if W is an affine subspace, and if I have two vectors in it, let's say W1, W2 in W, and if I were to take a t between 0 and 1 and interpolate these two using that t, then 1 minus t W1 plus t W2 is again a vector in W. So in this picture, say I take two vectors in the red line. Okay, these two are my two vectors. Well, if I were to lerp them, I'm just moving along this line. That's what that means. Lerp. Okay. Now here's a more advanced context in which affine subspaces are useful. We still have affine transformations, but let's not worry about that for now. Let's think about the space of 2 by 2 matrices. That's a 4-dimensional vector space. So V is space of 2 by 2 matrices. And let me let A to be one specific 2 by 2. Now let's say one of these matrices we know, let's say 0, 1, 1, 1. A specific vector in this space. Let me try to visualize what is happening. I want to think about the following line. I want to think about span of the identity matrix as a vector, and then minus A. This is an affine subspace. Think about the affine line, in fact, I can say, because it's spanned by one thing. Oh, I'll keep this. So this V is a 4-dimensional space, okay? Because I'm looking at the space of 2 by 2s. I'm still going to pretend that it's 2-dimensional, and I'm going to try to draw a picture. Okay. At the center is the 0 vector. In this context, it is the 2 by 2 0 vector. Okay. That's at the center. That's a 0 vector for the space. Then I look at the span of 1, 0, 0, 1. I don't quite know where this 1, 0, 0, 1 is, but it's somewhere. Say it's here. Okay. In this context, I'm thinking of this 1, 0, 0, 1 as a vector in and of itself. When I look at the span of it, I'm going to get the line passing through the origin and 1, 0, 0, 1. Okay, so this is the span of 1, 0, 0, 1. And again, in this picture, I don't quite know where A is, but it is somewhere. Okay, so say A is here. Here's A. But I'm going to subtract A from this line, meaning I'm going to translate it this way. I figure out where minus A is. It's at the opposite direction. Here's minus A. This is minus A. And so this affine line is the line that I get by taking this span and moving it this way using this vector. Pretend that these two lines are parallel. Okay, so this is this span of 1, 0, 0, 1 minus A affine line. By definition then, I can think of any vector, any 2 by 2 on this blue line as a matrix of the following form. Somewhere here, for instance, is lambda times 1, 0, 0, 1 minus a. Lambda is some scalar. Okay. As I vary lambda, I keep moving in this along this blue line. Now, here's where things get complicated. Inside this space of 2 by 2 matrices, I have this subset of invertible matrices. Okay? Not all matrices are invertible. For instance, the origin is not in this set of invertible matrices, but certainly identity is. The inverse of identity is itself, and so on. And in fact, it's not easy to see this, but the space of invertible matrices inside this is also 4-dimensional. Okay? So it's missing only a bunch of points. So I'll try to draw this like so. This is not an accurate description, of course, but so A also is invertible, we know. So maybe like this. There's like a gap here, like so. I wanted to keep this. This to be inside. Nope. I want this inside. I want that inside. It's also not one piece, in fact. So it has 2 pieces, 2 components. So I guess I should have not done this part. What is happening? I don't even know. Okay. I was just trying to draw a caricature of the set of all invertible matrices inside this. Okay? All invertibles. In fact, it's a, yeah.
Sorry, did you not include the origin just because in general?
It's not an invertible matrix.
Just never, okay.
Yes. Its determinant is 0. Determinant 0 means not invertible.
Right.
Exactly. I'm looking at the polynomial function, if you want, AD minus BC, and I'm looking at the non-zero set of this. Okay? The point I'm trying to make here is, you look at how this line, this specific line, skewers the set of all invertible matrices. Okay? And somehow, I'm kind of out of time, but this picture has to do with the definition of an eigenvalue. So the lambda such that this line is inside the orange region is the definition of an eigenvalue, essentially. This is very complicated at this stage. We're going to learn how to think of this more conveniently, but we're getting there. Okay, thank you. All right, let's start. Good morning. I'm going to take attendance. Write it here too. So we have a couple of things to discuss. I want to finish discussion of this example that I started talking about yesterday. We were thinking of as our vector space, the space of 2 by 2s. Okay. I took one matrix, the specific one. This was the Fibonacci propagator, if you remember from week 1. We had this Fibonacci rabbit model, and somehow we figured out, based on our assumptions, this was the matrix that we had to apply to state n to get state n plus 1. That's why I'm calling it the propagator. What we were doing is we were looking into this affine line given by the span of the identity matrix translated by this specific, by minus this specific matrix. So I'm not going to try drawing it again, but there's a point that I want to make. So the span of 1, 0, 0, 1, I take this, so it's a subspace of V, 2 by 2s, but then I translate it using this A. Okay? The question is this. That's what I was trying to do yesterday, but the issue is, in this 4-dimensional space of 2 by 2 matrices, well, some matrices are invertible and some are not. Which means that inside this 4-dimensional space, I can think of the set of all invertible matrices or non-invertible matrices. And I can try to visualize how this affine line is positioned. So this is all invertibles. This is all 2 by 2s. And somehow this affine line looks like this somehow. Okay. I want to figure out how these two things look. In other words, I want to figure out which 2 by 2s in this affine line are within or without this set of all invertible matrices. Now, this is a general fact that is not quite straightforward to see at this stage, but you would need some calculus and so on, and it turns out that you can do calculus with general matrices also. Let's just take it for granted. Pretty much most 2 by 2 matrices are invertible. Okay, that's what turns out to be the case. So instead of looking at those 2 by 2s in this affine line that are invertible, I want to look at the exceptions. In other words, I want to look at the 2 by 2s in this line that are not invertible. So I'll write this here, fact. A typical n by n is invertible. Okay, we can just take this as a fact. Most matrices are invertible, in fact, most square matrices. But some of them are not necessarily. If you were to take a random matrix, that would typically be invertible, however. In any event, I'm looking at those 2 by 2s in this affine line that falls out of this set of all invertibles. And so any 2 by 2 in this affine line I can think of in the following way. Any 2 by 2 in the affine line, span of identity minus A, can be considered, or is of the form, let me write, well, some scalar multiple of identity minus A. This is lambda. It's a Greek letter, Greek analog for L. This is kind of tradition. In this context, you can use whatever number, whatever letter you want, but it's more traditional in this context to use lambda as a scalar. So a scalar multiple of identity minus A, and when you do this, this turns into this, minus 0, 1, 1, 1. And this turns into this, lambda minus 1, lambda minus 1. Okay. So this is a 2 by 2 matrix that depends on one scalar lambda for some scalar lambda. For some scalar lambda. Any questions about this so far? Now, what can I say then? What can I, or how can I determine this lambda values for which this specific point in this line is outside the set of invertibles? So want all lambda values such that this guy, so lambda minus 1, lambda minus 1, is not invertible. Because most matrices are invertible, I want to look at exceptions. So what can I do here?
Use the formula for the determinant.
Yeah, so this week is all about this determinant. At least for 2 by 2s, we know the determinant formula, right? It is AD minus BC. So if you were to look at the determinant of this matrix, even though this is a letter, you can still multiply this by this minus this by this. So need determinant to be 0. Lambda minus 1. This by this gives me lambda times lambda minus 1, minus this by this gives me minus 1. Lambda squared minus lambda minus 1. So you see, to figure out which points on this affine line fall out of this typical set of invertibles, all you need to do then is to solve lambda squared minus lambda minus 1 equals 0. You would use, for instance, the quadratic formula. And indeed, if you were to use the quadratic formula, you would get 2 values for lambda. Lambda equals 1 plus or minus root 5 divided by 2. Lambda 1 plus or minus root 5 divided by 2. So exactly for these 2 specific scalars, this affine line falls out of this set of all invertibles. For all other lambda values, this line is in fact within the set of all invertibles. Okay? These lambdas, in other words, scalars lambda such that this specific affine line falls out of the set of all invertibles, these are called eigenvalues. I'll define it here. Value of A if lambda identity minus A not invertible. For now, you don't need to worry about this, but toward the end of, I think after the second midterm, we're going to have a whole week where we're going to start discussing these. So after the second midterm, the whole class is going to be all about eigenvalues, and there's an associated idea called eigenvectors. It turns out that there are certain technicalities. In this case, things are nice because you see this matrix is symmetric. You see when you flip it, you get the same thing. So this is symmetric. When you have a symmetric matrix, these eigenvalues show up nicely. If you don't have a symmetric matrix, things could be more complicated. And it turns out that in general, we're going to need to think about scalars that are possibly complex. Okay, things are going to get nasty at some point. For now, we don't need to worry too much about these matters. I just wanted to mention. It's like a rather nice context in which these affine lines show up. Okay. Any comments or questions about this? Okay. And later on, of course, once we start talking about eigenvalues, we're not going to try to visualize this like I tried to do yesterday. The set of all invertible matrices inside all matrices is kind of hard to visualize and so on. But at the very least, we'll be able to compute the determinant of an n by n by the end of this week. Okay. So I'll erase this. I'm not going to define an affine transformation in general. I'll just give you an example. In the case of the plane, an affine transformation is pretty much a linear transformation, except you also get to move the origin. Okay. So affine transformation is the same thing as linear transformation, but you also get to move the origin, move 0. So here's an example. Let's just try to visualize this. Well, let's say A is taking an xy and sends it to this. Okay, that's the formula for A. See, so far we hadn't seen an expression like this. You would just left multiply by a matrix. But you see, this is an affine transformation. So there's sort of like a translation part here. What people would say in this situation is, oh, this is the linear part, this is the translation part. And this is the translation part. That's an example. Let's try to visualize what this guy is doing. Well, first of all, if you want, we can consolidate this and use it, write it in tuple notation. So I can write it like so. This matrix multiplied by this, and then 0, 1 added. Okay, when I do this multiplication, I get minus yx plus 0, 1, which means that's what A does. Takes xy to minus y, x plus 1. You see, so far, if you're thinking about linear transformations, you never see scalars by themselves. They're always multiplied by a variable. In the affine case, that is allowed, however. And if you want to write this in tuple notation, you would write it like this. A of x comma y equals minus y comma x plus 1. Same thing. Okay. And how do you visualize things like this? My standard method, as usual, is to draw sort of like a face and see how it transforms. Okay. So I'm going to take, as usual, this guy. And I want to see what A does to it. Just like with linear transformations, affine transformations too take lines to lines. Okay? So if you want, if I want, I can just keep track of the edges where they go. But even before that, I might as well try keeping track of the vertices. So if I were to track 0, 0, the 0 vector, right, x0, y0, that is sent to 0, 1. Okay? So it goes to here. You see, this never happens with linear transformations. This can happen only with affine transformations. Or maybe more complicated things, of course. But we're not going to think about more complicated functions. What else? Well, 1, 0. Let's use a green box. If I were to plug in 1, 0, let's do this by hand perhaps. A 1, 0 goes to, so y is 0, 0, 2. Okay, so this box goes to this point. Okay. You keep going like this, and it turns out that this guy transforms this into this. Okay. So if you want to think about what this says, or if you're trying to verbalize what this guy does, well, it first rotates by 90 degrees in the counterclockwise direction, and then translates everything by 1 unit in the y direction. That's what you can imagine. Okay. So this way you get to combine a linear transformation and a translation to get more complicated functions and so on. It turns out that you can still pretend that affine transformations are linear, but that requires something called homogeneous coordinates. If you're interested in these kind of things, it's in the textbook under the computer graphics section. I'm not going to spend more time on this because we're already sort of behind schedule. So, can pretend affines are linear, so homogeneous coordinates. Under the computer graphics section in the textbook. This is a beautiful topic. Lots of interesting stuff under that section. Perspective projections and so on too. There are other things. But it's one of the optional topics that I think I'm going to let go and not discuss any further. Any comments or questions about this? I hope you can see the value of being able to translate things as well, because even from a computer graphics point of view, you would have sort of these models of, let's say, 3D models of certain objects, and you would have your world, but your models would be somewhere else. Let's say you have a barrel or whatever, and you want to put multiple barrels. Well, you're going to have to sort of move it on the side or to the side and so on, up, down, or something like that. Not only just rotations. Rotations would be just linear transformations, but you would need to move them around also. So that's why you would need translations like this, even to generate a nice scene. Okay, that's that. Now, I want to spend the rest of today with these two matters, elementary matrices and LU-type factorizations. Now, if you try to read the textbook regarding the LU factorizations, I think it's rather confusing. So I want to go back to this example I wanted to discuss last week to exemplify what is underneath this LU-type factorizations. First of all, just like with number multiplication, an important thing is number division. Okay? So for instance, if you have an integer, maybe you want to sort of factorize it into its prime factors. That ends up being important in cryptography and stuff. Well, we have matrix multiplication, which means that we want to sort of split one matrix into its factors as well in terms of matrices. So factorization is an important thing whenever you have a multiplication. So you want to do some sort of a factorization. When I say LU-type factorization, that means it's a whole family of different types of factorizations. There's LU, there's LDU, there's PLDU, and then there's a couple more. But they all depend on two fundamental ideas. Okay? First idea is that, well, row reduction, in fact, underneath the hood, is nothing but matrix multiplication. In other words, to each elementary row operation, there corresponds a certain type of matrix that when you multiply whatever matrix you're trying to row reduce by that matrix, the result is row reduction. That's the first idea. So, LU-type factorization means factorization of matrix A, some matrix A, using row reduction, essentially. If you take a more advanced linear analysis course, linear algebra course, maybe numerical linear algebra or something, you would also analyze the complexity of such matters. It turns out that instead of solving an equation, first factorizing your matrix into LU ends up being slightly more cheap. So there are many sort of reasons why you would want to factorize a matrix instead of doing standard row reduction by it. But we're not going to get there. Factorization using row reduction based on two ideas. Okay. Idea one is what I said. To each elementary row operation, there corresponds a matrix multiplication. So idea one, elementary row ops are matrix multiplication, are actually matrix multiplication. The second idea is slightly more cryptic, but bear with me. It turns out that there are certain types of matrices that can be grouped together. In other words, there are things called matrix groups. So some matrices can be grouped together. In terms of multiplication. I'll say more about the second item in a second. Let's first focus on understanding what item 1 means. And I'm going to actually switch over to an example. This example that I wanted to discuss last week. So here's the example again. So here's my A. It says 3 by 5 minus 6 minus 2 minus 4 minus 1 2 5 1 3 8 minus 7 minus 1 minus 4. Okay. Let's say we're trying to row reduce this. Ultimately, in this LU type factorizations, U, at least in the vanilla version, is an echelon form of A. Okay? There are different versions of this, but that's the vanilla version. So I want to turn it into, well, to this probably we're not going to be able to reduce, but I want to sort of, at the very least, row reduce this. And I did some calculations here, and I want to keep my calculations. So, let me see. So for instance, what I want to do is this first. I want to use minus 3 to get rid of this one and this 2. I don't want to have divided by 3 there. And so what I'm going to do is first I'm going to multiply the second row by 3 and then add the first row to the second row, okay, to row reduce. And so look at this. The idea is this. Multiplying the second row by 3 in the context of row reduction is the same thing as looking at this matrix. Okay? So first of all, this is 3 by 3. A is 3 by 5. When I do this product, I'm going to get a 3 by 5. Okay? Now, the rule is always the same. The left matrix you split into rows. The right matrix you split into columns. First row of my matrix here is 1, 0, 0. Okay? Take 1, 0, 0, and you're multiplying it against this. Okay? The end results are going to give me the first row of the product. But since this is 1, 0, 0, okay, this is going to be nothing but duplicating the first row. Okay? How about the second row? Well, now I'm going to take 0, 3, 0. Okay? Turn it this way. This time, I'm multiplying every single entry by 3. Okay? So this is now 3 minus 6, 6, 9 minus 3. Make sense? And likewise, if I were to take this third row, multiply it, it's just going to pick out the third row, and it's not going to do anything to it. So in a sense, what we were saying, what we were calling in the first week, oh, take this row and multiply it by some scalar that is non-zero, it really corresponds to left multiplying your matrix by an appropriate diagonal matrix. Okay? So in a sense, this is one of these elementary matrices that really corresponds to, well, scale the second row by 3. So scale second row by 3. Any comments about this or questions? Let's do one more. Of course, I can just at this point take the first row and add it to the second one to get rid of it, but to get rid of this 3. But let's leave it for now. I look ahead and I say, oh, eventually I'm going to try to get rid of this 2 as well. But again, I don't want to deal with fractions and so on. So what I'm going to do is I'm going to preemptively multiply the second row by 3 also. Multiply the third row by 3 also. So this time I'm going to take this matrix, okay? And in fact, let me call this E1. I'm going to take this matrix and multiply it by this. Okay? So I take this 3 by 5 now and left multiply it by this. Based on the same idea, okay, this is split into rows. If I were to take this, multiply it, it's going to give me the first row. Second row is going to give me the second row. And then the third row is going to give me 3 times the third row. Okay? So this time this is going to turn into this. Now this is 6 minus 12, 15, 24, minus 12. Okay? And I can call this, for instance, E2. So this diagonal with 1, 1, 3 then would again be a scalar, or scaling by 3, but instead of the second row, it would be scaling the third row. I'll write that too. So this was E1. E2 is 1, 1, 3. This is scale third row by 3. We have two other types of row operations. Take one row, add a scalar multiple of it to some other row, okay? So in a second, I'm going to give the matrix for that. And then the third one is going to be interchanging a bunch of rows. That is going to be the third type of matrix. Before going any further, I can now say a couple more words about the second idea. Well, what I can say is, just like I could have row reduced, or I could have multiplied both the second and third rows simultaneously by 3, I could have, instead of first multiplying a by e1 and then the end result by e2, I could have first multiplied e1 and e2 and multiplied a by that possibly more complicated matrix. And so this is that idea of matrix grouping. E2, E1 is this. The orders matter. Okay. When you multiply this, it turns out that this is this. So to me, this is an indication that you get to combine, you get to group matrices of the same type. In the sense that if you were to take two diagonals, well, their product too is going to be diagonal. So you can store a bunch of diagonal operations or a bunch of scalars, scaling operations, into one matrix. Okay? So this means we can group diagonal matrices together. So product of diagonals is diagonal, so we can group diagonal matrices together. So product of diagonals is diagonal, so can group diagonals together. I'll do one more step to give you yet another example of these elementary matrices. So for instance, at this stage, I can take this guy and add the first row to the second row to get rid of this 3. Exactly. My idea again is to be able to describe that operation in terms of a left matrix multiplication. So maybe like this, like this. Here's one more. So I need to start with this matrix to begin with. So instead of looking at A, I'm going to look at E2, E1A. Okay. And here I want to engineer a matrix that corresponds to taking the first row and adding it to the second row. That means that I'm not going to do anything with the first row, which means that the first row here is going to be 1, 0, 0. I'm not going to do anything with the third row, which means that the third row here is going to be 0, 0, 1. To add the first and second rows and add it and put it into the second row, I need to look at 1, 1, 0, in fact. Okay. Again, let's go through this. You take this, okay? This is the left matrix. Turn it into rows. Take this row, and I'm multiplying. Because this is 1, 0, 0, this is going to pick out only the first row. So the first row is fixed. Likewise, the third row is fixed. However, let's see what the second row turns into. I take 1, 1, 0, okay? 1, 1, 0. Okay, multiply, add these two together. That's 0, 0, 5, 10, minus 10. Okay. Like this. 5, 10, minus 10. And so this, let's call it E3. And so you see, scaling operation corresponds to left multiplying by one of these diagonals. Replacing or replacement operation corresponds to one of these matrices with ones on the diagonal, and either it is 0 above the diagonal or 0 below the diagonal. In this case, since I've used the first row to do something with the second row, I got a 1 here. I got something below the diagonal. Yeah?
So the opposite operation, where it'd be like using row 2 on row 1, would be the middle top value?
So you're, let me think. So you're saying take this and add it to this?
Yeah.
So for this operation, let me think. Yeah, it will be this.
So it's like the column the column is the one you're doing the operation on, and then the row
Exactly.
is the one that you're adding.
Yeah, exactly. Yeah, instead of adding the first row to the second row, if you wanted to add the second row to the first row to get rid of this minus 3, instead of left multiplying by this matrix, you would left multiply by this matrix, for instance. Okay. So this is lower triangular. This is upper triangular. That's a triangle you want to see. It turns out, again, these lower triangulars are also combinable. Meaning, if I were to take 2 lower triangulars, I'm not going to keep going with this calculation, but it turns out that if you were to take 2 matrices like this, multiply them, you're going to get back a matrix of the same type. And in fact, I'll write it here. So, for instance, let's say I take 1, 1, 1, x, y, z. And then 1, 1, 1, a, b, c. A, b, c, 0, 0, 0. Let's do this matrix multiplication real fast. Right, the first row stays. And then x plus a, 1, 0, z plus ay plus c here. And then here I have z plus by. This is ax plus c. Yeah, c, and then this is 1. So, OK, these numbers, they get mixed up. But ultimately, it's going to be of the same type. Okay. Lower triangular gives me lower triangular. So you get the lower, you get the group lower triangulars together also. Okay. Any comments so far? Again, let me reiterate. These lower triangulars or upper triangulars correspond to the replacement operation. Diagonals correspond to scaling. Lower triangular or upper triangular correspond to replace. Interchange is the third type. I'm not going to finish this row reduction, but I'll just do this. Say I want to take the first row to the second one. Oh, I'll just do it like that. Say I'm trying to interchange the first two rows. So I would need to take this matrix. I'll keep this. I have this here, and then I'm going to have a 3 by 3, and then I want the end result to be, well, first row this, second row this, third row this, for instance. So 0, 0, 5, 10, minus 10, minus 3, 6, minus 1, 1, minus 7, and then 6, minus 12, 15, 24, minus 12. Oh, I'm not going to do anything with the third row, which means that here I'm going to have 0, 0, 1. Out of this, to get, instead of this as the first row, what do I need? I'm going to take the first row here, and somehow it should pick out the second row of the original matrix, which means that this should be like this, and this should be like this. And this is a third type of a matrix. This is what is called a permutation matrix. A permutation matrix is a matrix that has exactly 1, 1 in each row and each column, and all of these are 0. It turns out that if you were to take any two matrices like this, multiply them together, you get back another matrix of the same type. So, permutation matrix. It permutes the channels in a sense. 1, 1 on each row and column, zeros otherwise. Permutation times permutation gives you another permutation. It turns out, you can just write down the formula, whatever, which means that, again, you can combine permutations. Meaning, instead of only sort of replacing these two, you can replace these two and then these two and so on, and that will give you, in total, one big permutation matrix. So can group permutations also. Okay. Now, this is essentially all there is to it when it comes to LU-type factorizations. Depending on how you want to sort of see these different types of matrices, permutations, lower triangulars or upper triangulars, and diagonals, and in which order you want to see them, well, you would do the row reductions in that order. Okay? And matrix-matrix multiplication is not commutative, meaning it matters in which order you do matrix-matrix multiplication. Sometimes it might happen that, oh, maybe you do one diagonal and then two lower triangular and then one more diagonal and so on. There are sort of methods to move these orders around. It's a calculation essentially. And depending on the context and depending on the application, you may want to choose one specific LU-type factorization over another one. So if you were to look at the Wikipedia page, you're going to see like 5 billion different ways of LU factorizing things. Okay. Okay. There's a couple more things I could say about this, but I don't think it's going to be illuminative or illuminating to discuss more.
May I ask some clarifying questions?
Yes.
So first base thing that we need to understand is that you can't just multiply anything by anything because it's not because matrix multiplication isn't commutative.
Yes, exactly.
But if we have things of the same type, then we can.
Yes, and then you would combine.
And then
Yeah.
and then it is actually commutative.
Yes.
If they're the same type.
Not necessarily, even then. So if you were to multiply these the other way around, the coefficients are going to be different. But at the very least, when you group them together, it's going to be one matrix of the same type.
So in that case, why are we trying to group them by type? Why not just, because they're all going to be, in this case, they're all 3 by 3s. So we
Yes.
still end up with a 3 by 3 at the end.
Yeah, that's a fair question. Because ultimately, say you ended up with writing something like this. A equals, let's say, one permutation, one lower diagonal, one lower triangular, one diagonal, and then one reduced. Okay? And so you read in this direction. This will tell you sort of like the back end and the front end of the transformation that is A. Say R is the reduced one. Say it is row reduced. That tells you the rank and nullity. Okay? That fixes how many vectors there are in the null space, how many vectors there are in the column space, essentially. But then you stretch the column space, for instance. Okay. Initially, you didn't have any stretching, but we know diagonals are about stretching. That doesn't sort of mix up the axes. Then you shear. Okay, you sort of do these geometric transformations one by one. And then finally, you sort of permute a bunch of axes if you want. That's sort of perhaps the idea.
So maybe to summarize your point, it's a convenient way of writing the data so that we can easily understand it.
That's one of it, yes. And another thing too is that if you can factorize something like this, there's a computational efficiency when you're trying to solve a system with A on the left-hand side also. Yeah. They kind of talk about it in the textbook, but they don't go too much into detail. Like I said, you would need to take sort of like a numerical linear algebra class to really understand what is happening. Okay, that's it for today. We're going to continue tomorrow. Thank you. All right, let's start. Good morning. So today we're going to start talking about determinants in more detail. I wanted to say a couple more words about a couple of things that we've been discussing so far. So first of all, we were yesterday talking about this lower triangulars that you can sort of combine them together. You can group them together. Meaning, if you were to take two lower triangulars with one on the diagonal, then the product of any two such matrices too is going to be of the same form. And at the end of class, one of your colleagues came and told me that this entry was wrong, what I computed. So initially, I think it was correct, and then I changed it. This is how it should be. And while we're here, we might as well see that these, so the order matters here. CB 1, 1, 0, 0, x 1, 0, z, y 1. When you multiply them this way, you get this, and then you get x plus a again, 1, 0, 1, and then y plus b, and then in this bottom left entry, I have c plus z plus xb. So you see this, instead of ay, I have xb. Okay. Meaning, in general, if you were to take two lower triangulars, the order in which you're going to multiply them, well, it's going to matter. Okay. And that's the only difference, really. Okay, I just wanted to clarify that. In fact, there's another interpretation of these. Well, instead of looking at lower triangulars, people typically look at upper triangulars, but the idea is the same. These are what are called the Heisenberg matrices because somehow it has something to do with Heisenberg uncertainty principle perhaps. Well, the person who came up with uncertainty principle, not necessarily uncertainty principle by itself, although I can imagine some sort of a connection. It turns out, for instance, maybe this entry corresponds to something like a position operator in quantum physics, and this entry corresponds to a momentum operator, and so on. So somehow, in all these different areas of science, especially in physics, people look at specific matrices and they see significance with very straightforward matrix-matrix multiplication equations. Okay. So if you want to look into this, this is like Heisenberg stuff. Okay. An exercise regarding these different groups. So we had one group which was these diagonals. Another one was lower triangulars. And I told you there are certain tricks that you can use to switch the orders of two such matrices. It's a very nice exercise to try to figure out what you can use. For instance, imagine something like this. 1, 0, 1, and then x, y, z. You have three variables like that. This is lower triangular with ones on the diagonal. And let's say next to it you have a diagonal matrix. Okay. Say you're trying to change the orders of these. Well, in general, it turns out that it's not quite straightforward to guarantee that these numbers are going to be the same, but still you can keep the general form. Meaning, take this and turn them around with different variables possibly. Say a bar, b bar, c bar here, and then x bar, y bar, z bar. The point of this exercise is to solve for a bar, b bar, c bar, and x bar, y bar, and z bar in terms of the other guys. Solve for bar variables in terms of the other ones. In terms of the other variables. You just do matrix-matrix multiplication on both sides and you equate. For instance, it's going to turn out, once you start opening this up, is that in fact a bar equals a, b bar equals b, c bar equals c. But somehow x bar, y bar, and z bar are going to depend on x, y, z and specific combinations of a, b, and c. So if you wanted to, instead of first doing scaling, if you wanted to do replacing, well, you can, in fact, do that, but it has a cost. There's a trade-off. You're going to have to change the scalars with which you're going to have to replace things. Okay, it's a nice exercise, and there are other exercises like this. But this, I think, gives a flavor of the types of things you end up needing to do if you want to do like LU-type decompositions properly. Okay. Any comments or questions about this? Okay, now I want to say a couple more words about these different groups. And more specifically, I want to talk a little bit about this other notation, namely the notation they use for matrices in the context of machine learning or large language models, just so that we have some more literacy. We're more comfortable with more notations. So this is the ML notation. I'm going to abstract a bunch of things. Things that are more complicated in general. Just going to look at a simple situation. Say A is 3 by 4. Okay, it's a 3 by 4 matrix. Maybe we can just write it like this: A11, and then A14, and then A21 dot 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 A24, A31 dot 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 A34. Okay, I didn't write the middle two terms. In machine learning, an equation like this is described in terms of certain channels. Okay? As usual, I'm thinking of A to be a linear transformation from 4 dimensions to 3 dimensions, which means X is a vector that has 4 components, Y is a vector that has 3 components. Okay. Now to describe this, in machine learning, you would see diagrams like so. You draw, so you think of these scalars as separate channels, separate input channels, and these as separate output channels. And you put them like this. Okay, and then y2, y3, y4, okay? So this is the input layer, and this is the output layer. Again, I'm just looking at a very simple situation. In practice, things are more complicated. Now, how do you represent A? That is the more important part. Well, you say,
Dr. L,
yes.
in your original equation on the bottom left, you wrote 3, so y having 3 rows, and then
Oh.
with the y having 4 rows.
Thank you. Yeah. Very good. So that should be x4 and y3, and I should have this. Okay. Apologies. Yeah, thank you. So the point is, how do you represent A? Well, the first row, you say, or rather, you look at the outputs, okay? The first channel, when you multiply, well, it's going to have some contribution coming from each of these channels, okay? And then the first row, which I circled in blue, basically combines all 4 of these channels and puts them in y1. And so you would denote this like this. Okay? That represents the first row of A. The second row, let's use orange. Again, turns into this. And then the third row, which I'm going to use red to denote, is this. Okay. Now, in machine learning, typically instead of using a linear transformation, you use an affine transformation like this. So this would be one layer, this would be another layer, and then typically you have many layers like this, and you have many linear transformations that you sort of keep left multiplying. Okay? And furthermore, the interpretation is that each of these channels really are neurons, and somehow, based on some biological theories and so on, neurons need certain some activation. So instead of just compositing a bunch of linear transformations like this, well, you would start with one linear or affine, going from one layer to another, and then when you're switching from the Y layer to, say, Z layer, you would in fact apply some sort of a small nonlinear transformation to each of these channels. Okay? There's a bunch of choices for these, but the big theory is that just sandwiching a bunch of linears together with nonlinears allow you to express whatever function you want to express. And that's the main idea of machine learning, essentially. There's a bunch of architectures and so on. Let's not get into that. All I want to talk about is this diagram, okay? Because I know some of you are looking into machine learning stuff. In machine learning literature, you would see sort of pictures like this quite often. It's nothing different than matrix-matrix or matrix-vector multiplication. They just draw it differently, okay? Any comments so far? Now, I want to use these diagrams to talk more about these three different groups of matrices: permutations, diagonals, and lower triangulars. And instead of going from 4 dimensions to 3 dimensions, I'm going to keep it 3 by 3 because all of these are ultimately going to be invertible matrices. In machine learning, you use more general matrices, of course. So you see, this picture, in the general case, looks very complicated in a sense. But if I were to focus my attention to any one of these groups of matrices, the machine learning caricature ends up being a lot more simpler. So for instance, let's start with diagonals. Well, I'm going to have 3 like this, 3 channels on the input, 3 on the output. Well, if you have a diagonal matrix, well, what's going to happen is the first output is only affected by the first input, okay? And like this and like this. Does this make sense? So you say, oh, so imagine something like this. 2, 3, minus 5. So this corresponds to multiplying by 2, whatever this input is. This corresponds to multiplying by 3. This corresponds to multiplying by minus 5. So you see, the machine learning notation is a lot simpler for diagonals. And of course, if I had 2 diagonals like this next to each other, well, I would have one of these like this and another one next to it. And then when I multiply, I would get again a diagonal. Okay. So composite of diagonals is diagonal. Okay. Does this kind of make sense? With permutations, things are pretty much the same, except that there are certain crossings. Okay? What's a permutation matrix? It's a square matrix such that all of its entries are either 0 or 1, and on each row and each column there's exactly 1, 1. So 1, 1 on each row and column. Just do this like this because I want to put lower triangulars here also. 1, 1 on each row and column. Toward the end of the course, if time permits, we're going to talk about a generalization of permutation matrices, namely Markov matrices, or Markov matrices that end up being very useful in applications. But for now, we're just looking at perms. In the case of 3 by 3, in fact, there are exactly 6 permutation matrices. You can just write them down. And in fact, I'll do it here. There's 1, and then, okay, I'll be systematic a little bit. Like this, and then like this, and then I have 0, 1, 0, 0, 0, 1, 1, 0, 0. I have 0, 0, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0. These are all possible 3 by 3 permutation matrices. As you see, on each row and on each column, I have exactly 1, 1. Okay. In general, n by n's, in the case of n by n's, you would have exactly n factorial permutations. In any event, in machine learning notation, let's try to draw these. Like so. I'm going to add the connections in a second. These are different channels. Okay. This doesn't do anything, so it's pretty much the same as before. This one, you see, it doesn't do anything with the first channel, but it interchanges the second and third channels, which means you're going to have a cross there. Okay, so it's going to be like this. Does that make sense? This, I again look at immediately which channel is fixed. The third channel is fixed, and I'm flipping the first two. This one fixes the second channel, mixes the first and the third. These two are the complicated ones. Let's think about this. Where should I connect the first channel here? Second? This one? This one. How did you guess that? Well, let's think about it like this. Maybe you're right, but I need to check it. If you're confused, well, you go back to matrix-matrix multiplication to figure out where you should be sending the first channel, or you're just going to feed it the first standard vector. Well, when you do this multiplication, this is just going to give you this. Yes, which means you need to send it to the second one. Make sense? Was this what you said? Or? No. Okay. Okay. So this is what happens. And again, this specific matrix sends the second standard vector to the third, which means this is how it operates. Okay? And then there's this. First goes to the third, second goes to the first, third goes to the second. And these diagrams we're always reading from left to right. Of course, you can do it the other way around too, but you want to read it this way. Input on the left, output on the right. Any comments or questions about this so far? And like I said, you can sort of put another layer if you want, and that would correspond to matrix-matrix multiplication. In the case of diagonals, even though it tells you that the product of two diagonals is diagonal, it doesn't quite say the numbers themselves. Well, you would say, I guess, if you have something like this, if you have two wires like this, You need to multiply the corresponding numbers to get the corresponding entry in the product diagonal matrix. I find it very useful to use these machine learning symbols or notation to come up with products of permutations. So for instance, let's say I want to square this guy. Or maybe I want to multiply this by this in this order. Okay, and then this, this, this. Of course, I can go ahead and multiply. And in fact, let's do this really fast. This is 1, 0, 0, 0, 1, 0, 0, 0, 1. So it's the identity matrix. Okay? This is the standard matrix-matrix multiplication. The point of these symbols, the machine learning notation is, if you use the correct notations, well, you're going to be able to read off what should be happening also. So here's the idea. Even though, of course, we're reading these diagrams coming from machine learning from left to right, when you're doing matrix-matrix multiplication, first you're applying this, and then this. Okay? So we're reading matrix-matrix multiplication that way, in a sense, if you want to think of these as transformations. Okay. Okay. So first, this is the first layer. It is this guy. Okay? This guy looks like this. Okay? And then this is a second transformation, which means it's the second layer. This one looks like this. Now I'm going to chase the connections. Okay? So if I start with the first channel, again, I'm reading from left to right this way. If I start with the first channel, I see which channels are affected in the second layer, and then I'm going to keep chasing it. So you see, if I start at the first, then I end up at the first. Okay? If I start at the second, I end up at the second. Sort of bounce like this. If I start at the third, I end up at the third. Meaning, if you were to composite these two transformations like we computed, the end result is going to be the identity transformation. Yeah?
And that's only because the identity matrix is the final one, right? If you had like a different matrix, it wouldn't map so perfectly.
Yeah, it might be something else, exactly. Yeah. Yes. Yes. Yeah, so if I were to sort of square this, you would get something else. In fact, I think you would get one of these single crossing situations. Any comments or questions about this? Okay. Let's perhaps say a couple words about this lower triangulars as well. Again, lower triangulars are going to be slightly more complicated, even compared to diagonals. So I'm looking at a matrix of this form this time. But you see, there's still some simplicity to the diagrams this time, because the first output is only affected by the first input. Okay. The second is affected like this. The third is affected like so. So somehow, in the case of lower triangulars, the lower your channel is, the more things it is affected by. The higher it is, the fewer inputs it requires. Yeah?
Sorry to go back so far, but I've been looking at the perms, and it looks like the top right and middle right
diagrams might be switched.
Um,
Correct me if I'm wrong. Right.
so you're saying the picture should be the other way around?
Yeah.
Um,
Because the top one would be going down to the bottom. Yeah. Yeah. On the first one.
but but this takes 1, 0, 0 to 0, 1, 0, no? When you left multiply?
Oh, yep, I am backwards.
Yeah. Yeah, the fast way to think about it is, remember, when you're trying to understand a transformation, first column is where the matrix sends 1, 0, 0, 2. So E1 is sent to E2, E2 is sent to E3, E3 is sent to E1. Does that make sense? Yeah. Yeah, it is very confusing. Yeah. Good point. Any other comments or questions about these? Okay. Like I said, in machine learning, when you look at literature, there's a bunch of diagrams like this, but it's as simple as that. They're just trying to sort of visualize somehow matrix-matrix multiplication, because they have like lots of matrices and so on. Okay. That's it. So we're done with the previous chapter, matrix algebra, and we can talk about determinants. I want to first start talking about dimension, though, a little bit more. I wanted to talk about this before, but now it's going to come in very handy. Because somehow you can think about determinant as something, it's a function, or it's a number that you can associate to any square matrix that has some mysterious properties that end up being very useful. But in a sense, it has a very intuitive meaning. Okay? The way I imagine this, because I like calculus more perhaps, is, well, determinant of A, a square matrix, which I interpret as a linear transformation, is the volume distortion factor. Okay? Which means that we need to understand a little bit what volume is, and for that we need to understand a little bit what dimension is. And so here's a more intuitive idea of dimension. So this is chapter 3, determinants. So first, dimension. Again, perhaps. We know, of course, if I have a subspace, the dimension of that subspace is the number of basis vectors. Okay? Any subspace, let's remind ourselves, has multiple bases, but even though there are multiple different bases possibly, the number of vectors in any basis turns out to be the same. And that same integer was a dimension. That's how we defined it. But here's another way to think about the dimension. I want to say something like this, okay? Say I have a one-dimensional space, one-dimensional vector space. It's a line. I'm going to take a small patch of it. So it's a line segment now. I got rid of this infinities and so on. I look at this small segment. And I want to make sense of the idea that this has dimension 1. Here's what I can do. I can think of pixelating this line segment into smaller pieces. Okay? And I'm going to say, oh, let's say I have a bunch of pixels, and each of these pixels have side length or length 1 over n. Let's say this whole thing has length capital L. It doesn't really matter. You're going to see. Because somehow, you see, the dimension of this shape should not depend on the length of it, insofar as the length is positive. So you pixelate this into a bunch of pixels. Okay? And you say each pixel has length 1 over n. So size of pixel over n. Then you say, well, if I have a bunch of pixels, each of size 1 over n, how many pixels am I going to need to describe the whole thing? Well, if one of these has length 1 over n, well, in total, the length is L, which means that I'm going to need n times L many pixels of this size. Number of pixels needed, in this case, n times L. And so somehow, you don't see it here, but the dimension, which is supposed to be 1, is the exponent of the size of the pixel I should be taking to have this equation. So number of pixels, number of size 1 over n pixels times 1 over n to the d is constant. I don't really care about this constant. In this case, it's L, but that's not really important for dimension. In this case, you see d ends up being 1, because this we saw is n times L, and this is this. In order for this to be a constant, somehow this has to cancel out with this, which means that in order for this to be constant, d has to be 1. Meaning, based on this comparison between size of pixel and number of pixels needed to cover the whole thing, you can recover the dimension. Any questions about this so far? Of course, I'm going to do this with 2 dimensions to make a little bit more sense. In 1 dimension, it doesn't really make sense as far as I'm concerned. If I had a small patch that is supposed to be 2-dimensional, it's going to be rectangular like this. Again, I'm going to try to cover it using pixels, little boxes, okay? So like this. Okay? If the size of each pixel, meaning the side length of each pixel is 1 over n, how many pixels am I going to need this time, approximately, to cover the whole thing? Let's say this is a rectangle, this is a square of area 1. How many would I need?
Number of pixels.
But if I had one of these boxes, 1 over n, if I had n, I would just cover this part.
N by n.
N squared. Yeah. Okay. So the number of pixels this time should be n squared, 1 over n. And again, up to some d, I want this to be a constant. In order for this to happen, d has to be 2, so that it cancels out with this. Now, it turns out that you can do this pretty much with any shape whatsoever. And that's really yet another way of defining dimension. So, in general, for, let's say, R a region like this, shape, say n sub n is the number of pixels of side length equals 1 over n needed to cover R. Cover R. Then dimension of R is the d, is the number, such that n capital N sub n times 1 over n to the d is constant. Not exactly necessarily, approximately constant. There are certain limits really here, but we don't need to worry about that. Okay. So somehow this is yet another way of discovering the dimension without even knowing anything about linear algebra. You can actually solve this for d and take certain limits if you're familiar with those kind of matters, but let's not get into that. All I'm trying to say here is that somehow this is yet another way of imagining the dimension. And based on this, now we can perhaps talk a little bit about volumes. Okay. Specifically, this whole thing really says that this integer dimension, which actually in this context is not necessarily an integer, but never mind. For our purposes, dimension is always an integer. You can think of d as how volumes scale. Meaning, in a d-dimensional space, say, ball of radius r has volume that scales approximately like r to the d. This is an important thing. Okay. So for instance, in one dimensions, if I were to take an interval of length r, its volume in one dimension, of course, is length. Well, it grows like r to the 1. In two dimensions, pi r squared, okay, I don't want to worry about pi. It grows like r to the 2. In three dimensions, there's a formula I don't even remember. But somewhere in there, it depends on the radius as a cubic, okay? And so dimension is that power law. It tells you, really, as you're increasing the radius of a ball in whatever space you're looking at, how does the volume change as a function of the radius? Dimension is a power law. Okay. And now I can talk about determinants. This is how I imagine determinants. Definition. Yeah. Let A be n by n. I have an n by n matrix. In other words, I'm thinking of a linear transformation from n dimensions to n dimensions. When I say n dimension, again, based on this volume understanding, I should realize that the volume of a ball of radius r in n dimensions should be like r to the n, up to some constant. Then determinant of A, okay, is a number, is a scalar. That is the volume distortion coefficient. that is the volume distortion coefficient. Meaning, I take a region R in n dimensions and compare its volume to the volume of the image of that region under A. So take a region, take a box B in Rn, so positive volume, then determinant of A is, well, the ratio of the volume of the image box versus the volume of the original box. It's kind of a miraculous thing, but somehow this expression ends up being constant in the box. Doesn't depend on B. Before going any further, let's try to figure out determinants of certain matrices based on this description. I'm doing all this because the algebraic definition of determinant doesn't really make much sense initially. But it's a very intuitive idea, in fact. So an example. Say A is 2, 2, 2, 2, diagonal. What is this determinant? Take a box, apply A to it. Okay. Your box is 4-dimensional. When you apply A to it, well, it's the same thing as scaling it by a factor of 2. When you scale a box by 2, in 4 dimensions, the volume distortion is going to be 2 to the 4. So the determinant is 2 to the 4. Which is 16. Okay. Any comments or questions about this? So maybe I'll say something. So applying A corresponds to stretching by a factor of 2, so stretching the box in all directions, okay, in all directions by a factor of 2. Box is 4-dimensional. 4, you put it in the exponents, okay? So for D, so volume scales by 2 to the 4. That's the intuition behind this calculation. Any comments or questions about this? Yes?
How is that related to the first thing you spoke about? Your first definition of dimension based on calculation.
Well, the idea there was that dimension really is this power law. So dimension really is how the volume in that space distorts when you take and expand things. So whatever that integer is, in our case, you put it in the exponent. I'm saying all this because down the line, you're going to start doing calculations like this, and you're going to put determinant of A is 2, because like this is 2 times identity. Okay? Don't forget the 2. Don't forget the 4. Don't forget the 2 either. Let's do one more. Say I have different diagonal entries. Again, it's a diagonal matrix. Let's say 2, 3, 5. What is determinant? Yeah. You're saying 3? 30. Oh, 30. Okay. Exactly. Why? Because now this is a transformation in 3 dimensions. Take a little cube, okay? In one axis, you expand it by 2, multiplied volume by 2. And another axis, you expand it by 3, multiply again by 3. In the third axis, you expand by 5, multiply again by 5. So the total volume distortion has to be the product. And in fact, this is going to work for any diagonal. The determinant of a diagonal matrix is the product of the diagonal entries. Determinant of A1, A2, dot, 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 AN is A1, A2, dot, 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 AN, by the same idea. Make sense? There's a small issue still. There's a mistake here, minor mistake. In principle, determinant could be negative also, but certainly the ratio of 2 volumes can never be negative. So the proper way of thinking of this is it's the signed volume distortion. So there's also the minus, which we're going to make sense of later. Okay, that's it for today. We're going to continue on Friday. Thank you. All right, let's start. Good morning. We have Valentine's Day tomorrow. It's nice. And Monday is President's Day. Specifically, we're celebrating President Washington's birthday. So we don't have class on Monday. We're going to take a break. On Tuesday, we're going to continue from where we're left off from today. We were discussing determinants before going into the sort of algebra of it. I was developing certain rules coming from this idea that dimension essentially is a power law, and determinant really is the volume distortion coefficient. So we think of square matrices as transformations, and we're sort of like developing what sort of algebraic properties determinants should have based on this intuitive idea. So let me remind you some things. This whole idea of dimension as a power law was this idea that, well, you take a region, a shape, let's say a shape, doesn't really matter what the shape is. And I take a positive integer, n, okay? And then we were trying to cover the whole shape R using small boxes with each side length 1 over n. So I called this last time pixels, but of course, maybe in 3 dimensions you want to call it boxes, whatever. So when I say pixel, I mean sort of like a metaphorical pixel. The point is that these 2 small boxes should not overlap. So n sub n of R was the number of pixels of size one over n needed to cover R. And in fact, I should say minimum number, but you get the point. Needed to cover R. Then the dimension of R was this number that solved this equation. So n sub n of R times 1 over n raised to the power dimension of R. We want this to be approximately constant. So the dimension really is, and this works in our situation certainly, is this exponent that you see. And if you want, you can, in fact, solve this for dimension using logs and stuff and get rid of this constant as well. So you would take, for instance, logs of everything minus, because that's in the denominator, dimension of R times log of n equals, let's say, or approximately, is log of some constant. Then you solve this for dimension of R. You move things around and so on. Dimension of R is approximately, well, this minus that divided by log of n. Okay. If you want to be more precise, what you do is, in fact, you take this expression, you take n to infinity, if you know calculus, so that this constant drops out. Doesn't really matter what this constant is, ultimately. And even then, it is not necessarily true that this log by log stabilizes. So you do something with that. In practice, what you do is, well, you plot n against n sub n of R. But in the log-log graph, so you plot log of n against this. So this is your horizontal, this is your vertical. As n goes to infinity, your pixels shrink, which means your resolution go to infinity. And so you draw log n here, log n sub n of R here. The larger the n is, the more pixels you're going to need. Am I correct? Yes. The larger the n is, the more you're going to need. So for each n, you have one data point here. Typically, you don't get this beautiful equality, whatever. You get something approximate. And then you make your computer plot the best fitting line here. And so somehow that line ends up being, or rather the slope of it ends up being the dimension. So this is a rather useful sort of algorithm that a lot of people use. And the true name for this is what is called box dimension. Because you take your shape and you sort of cover it with boxes and you count the number of boxes. For those of you who are interested in these kind of matters. We're not going to need this that much. But this intuition that dimension shows up in the exponents is important for us. Now, based on this, we said, oh, if I have a linear transformation from Rn, or maybe I should say Rd to Rd, then its determinant is going to be the ratio of the volume of one shape distorted under A by the volume of the original shape. So determinant of A is plus or minus, there's some sign that we're going to have to make sense of in a second, which we're going to do in a second, but for now let's not worry about it. Volume of image of, let's say, a region R under A divided by volume of the region itself. Okay, this is how we started thinking about it. Again, when I speak of volumes, because this is d-dimensional, you should think of d-dimensional volume. So typically we like to think of volume as like a three-dimensional thing. But for instance, if d were 1, by volume I really mean length. If d were 2, by volume I really mean area, and so on. Okay, so these are d-dimensional volume. Okay. Just to match this with our understanding of determinants in the 2×2 case, here's a nice exercise. In the case of d equals 2, two-dimensional volume is nothing but area, of course. So determinant of a 2×2, which is this AD minus BC, should be the area distortion coefficient. Okay? So d equals 2. And so volume is the same thing as area in 2 dimensions. And if I were to take a 2×2 like this, ABCD, we know that its determinant is AD minus BC. We had this algebraic formula. Okay. And so if I were to take a unit box like this, its area certainly is 1. So I can see how this A transforms this box and look at the area of that transformed shape. That area should be AD minus BC in absolute value. Okay, if this is correct. And so, of course, I can kind of draw a typical picture. Because A is ABCD, I know that the first column is where 1, 0 is sent to. And the second column is where 0, 1 is sent to. So I can draw sort of this typical picture. It's going to be distorted like this a little bit. Okay. Say your distortion is like so. So this is where A takes 1, 0 to. So the coordinates of this point is AC. Okay? So the x-axis here is A, y-axis is C, for instance. And likewise, the coordinates of this other point is BD. Okay so far? Now the content of this exercise is to compute that indeed the area of this parallelogram is AD minus BC in absolute value. The area of this shape is AD minus BC in absolute value. Okay. And how are you going to do this? You're going to sort of chop it into a bunch of things. You're going to do some sort of geometry, whatever. Right? So you sort of like chop it like this and so on. Sort of move certain pieces around. And that's how you would show, if you so desire, that the area of this distorted shape, right? So the numerator is AD minus BC in absolute value. The denominator in this case is 1. Maybe I should write that as well. Area of the original shape is 1. Okay? What I'm trying to say is the same idea works in higher dimensions. Okay? Any comments or questions so far? So taking this idea that determinant is nothing but volume distortion coefficient up to plus and minus, we realized, for instance, that the determinant of a diagonal matrix is nothing but the product of the diagonal entries. Okay? So the determinant of a diagonal matrix is very easy to compute. Okay? What else do I want to say? Yeah, so let's do perhaps one more example. The simplest matrices are diagonals. The next type of matrix that is slightly more complicated perhaps is the upper triangulars or lower triangulars. And in fact, let's try to look at one matrix with ones on the diagonal, like so, and say here I have a 10. What is the determinant? Based on our interpretation, that determinant is volume distortion coefficient. Remember this matrix we call the shear. You want to visualize what is happening. When I see something like this, for instance, I immediately realize that, oh, if this is a transformation in 3 dimensions, and so this is x, this is y, this is z. Oh, I meant this. Oh, okay, sorry. Yeah, sorry. Yeah. So this matrix fixes 0, 1, 0 and 0, 0, 1. Okay? These two are not going to move. However, as you see, the first column is where the matrix takes 1, 0, 0, 2. So if you were to take E1, A shears E1 in the z direction by 10 units. Okay? Maybe this E1 now turns into this. Do we see this? Okay. So if I were to take a unit cube, and if I were to apply a to it, imagine the x-axis is coming toward you. Here's my cube. Okay? If I were to apply a to it, what happens is, well, you're just shifting this side upwards. Well, from basic geometry, I hope you would agree with me. Well, insofar as this height doesn't change, the volume should be the same. Right? You can see this in 2 dimensions as well if you want. Right? So the area of this is always the length of the base times its height. When you shear, the area or volume doesn't change. So consequently, the determinant of this has to be 1. We're going to learn sort of this general formula, but it gets nasty, you see. So I want you to be able to compute determinants of certain matrices just by looking at them, okay? So if you have a lower triangular with ones on the diagonal, determinant is immediately 1. Likewise, if you had an upper triangular with ones on the diagonal, determinant would be 1 also. I'll do one more example here. Maybe let's do this, in fact. 1, 1, 1, like this. Let me make it more complicated. Say 2, 3, minus 5. Okay? So this was this picture. This is again a shear. It's more complicated looking than this matrix, but determinant hopefully is going to be again 1. So let's try to visualize what is happening. This is x, y, z. My matrix fixes E1. Doesn't do anything to that. My matrix doesn't fix E2, does something to it. And likewise, E3, something happens to. Okay? Now you want to take your time trying to visualize this matrix. First, let's look at how A transforms E2. 0, 1, 0. 0, 1, 0 is sent to 2, 1, 0. Meaning, you take E2 and shear it in the x direction. Okay? So this is my E1, this is my E2. Okay? When I apply A to it, E2 is going to be sheared this way. Okay? So this vector comes this way by 2 units. So this is parallel to this, and that's what it turns into. Okay? And then E3 is sheared in this bizarre direction. It's sheared in the negative direction for x, goes back, because that's a -5. And then it's sheared to a lesser extent by 3 units in this direction. But the height is going to be still 1. Okay, I'm not going to draw this, but when you apply A to this third vector, its height is going to be the same. It's going to move in this plane. So again, the volume of the unit cube under A is not going to change. Determinant has to be again 1. Okay? So we have more rules. Diagonals, just the product of the diagonal entries. Lower triangular with 1s on the diagonal, or upper triangular with 1s on the diagonal. These 2 cases. Again, determinant is immediately 1. If you're in this shape, so something is underneath, I don't really care. The moment you see the shape, determinant is 1. The moment you see it the other way around, so 0 is underneath, again, determinant is immediately 1. In any dimension, okay? Any comments or questions so far? It's a very good practice to think about determinant geometrically, but if you're having issues, you can just take these formulas as things to memorize. But I find it much easier to just try to visualize things and sort of remember that way. Now, there's a couple more things that we would like to be able to do, but to discover more rules, we need to sort of reinterpret or rethink this volume distortion coefficient and what it sort of gives further. What if I were to take the composite of 2 transformations? In other words, say I have A goes from RD to RD, and B that goes from RD to RD also. So that I can take the product, AB or BA, whatever, and that composite, that product, would be a composite transformation. Ultimately, determinant of AB also makes sense. I hope you would agree with me at this stage. It would be very convenient to be able to relate this to the product of the determinants. Okay? So let's say I have this. Say B, and then A, and this is the product AB. Okay? Well, let me start with Doesn't really matter that much, but let's start from the right-hand side. Say I have a shape or region, R, a shape here. I can push it here using B. Now I have BR, that's a region here, and push it here to get ABR. Determinant of B should be the volume ratio of these two, and determinant of A should be the volume ratio of these two. While the numerators, denominators, and so on are going to cancel out, which ultimately is going to give me equality on that side. Meaning, determinant, so let's write it in this order. Oh, determinant A times determinant B. Okay. So determinant of A, you see the point here is that I get to use whatever shape I want here. Okay? As long as it has positive volume. Determinant of A is the ratio of the volumes of these two things. So volume of ABR divided by volume of BR. And in determinant A, volume of this divided by the volume of this. Volume of BR divided by volume of R. What I was saying is, this cancels out with this, and I have the ratio of AB of R, or rather its volume, to the volume of R. And that's by definition the determinant of AB. Okay. Meaning, when you multiply two matrices, their determinants multiply, or in other words, when you're trying to take the determinant of the product of two matrices, insofar as they're square, you get the distributes. Okay? And so, using this idea, in fact, I can compute the determinant of an arbitrary, say, lower triangular. Say I have something like this, but maybe on the diagonal I have numbers that are not 1. So example, say A is 2, 3, 5. I think we had used this before. And then 10, 20, minus 3. Okay? How do I compute the determinant of this? You can try to sort of visualize what is happening geometrically as well, but ultimately, this is the product of one diagonal and one shear. Okay? Once you factorize it like this, shear is not going to affect the volume, which means determinant is going to be 1 from that part, but there's going to be a correction factor coming from the diagonal part. In other words, if you want, you can do it like this. Say I want to have lower triangular with ones on the diagonal here. I can factorize this by dividing the first row by 1/2, which means I have this. The second row by 1/3, which means I have this. And then the third row I can divide by 1/5, which means this entry is 10/3. This entry is minus 3/5, not that it matters. And this entry is 4. Okay, I can factorize it like this. Distribute. This is the determinant of this diagonal. times this lower triangular. I'm not even going to write down the other entries because it doesn't matter. They just shear in some directions. Well, this gives me, multiply by 2, then 3, then 5. So in total, this is multiplication by 30. And this is just going to be 1. So the determinant of this is, again, 30. Okay? Meaning, you can sort of put these two together and say, well, if I had an arbitrary lower triangular or an arbitrary upper triangular, its determinant is immediately the product of the diagonal entries. Okay. You still need to make sense of this plus or minus. I'm going to tell you a couple words about it in a second. For now, let's not worry about it. So, determinant of lower triangular so say lambda 1 all the way up to lambda n here, all zeros here, and some stuff here. This is lambda 1 dot 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 lambda n, the product. Determinant of upper triangular, some whatever here, zeros. Otherwise, it's the product again. Okay. These are two more rules. Now, when I say something like this, you cannot have stuff underneath and above. Okay, that's not lower or upper triangular. Things are more complicated in that situation. We still don't know how to compute the determinant of a general matrix, but we're getting there. Okay, I'm giving you special cases so that you can, just by looking at the shape of the matrix, in certain situations, you can just immediately say what the determinant is. Okay? Any questions or comments so far? Here's one more observation. When you're looking into the volume of a shape, you should be looking at the volume in the appropriate dimension. Meaning, even if you're in 3 dimensions, if you were to look at the 3-dimensional volume of a 2-dimensional thing, that volume should be 0. Okay? A plane doesn't have any volume. I mean, so this has a volume, for instance. We would like to imagine a plane like this, but if a physical object didn't have any volume, it also wouldn't have any mass, in which case it would not exist. So, and likewise, a line has no area, and it has no volume also, 3-dimensional volume. And so based on that, I can connect determinants to invertibility. Okay? Again, I'm looking at a linear transformation from RD to RD. Well, it's a square matrix. We know by now that A is invertible, has a multiplicative inverse, if and only if its rank, or R number, is the maximum possible, in this case, D. In other words, when you row reduce A, you should be able to get the identity matrix, or at least exactly D pivots. Invertible is the same thing as rank of A is D. But if that is the case, if you were to take a shape and apply A to it, insofar as the original shape has positive D-dimensional volume, the image 2, the distorted shape 2, is going to have positive volume. And the only way the image fails to have positive volume is if the rank of A is less than D, so that there's some squishing happening. Meaning, A is invertible if and only if its determinant is non-zero. Okay. Does this match with what we already know? Well, for instance, if you were to take a diagonal, okay? 1, 1, 0 on the diagonals. Okay, this should be 0. Because we talked about how the product, so the determinant of a diagonal is the product of the diagonal entries. If you have 1, 0 on the diagonal, that has to be 0. And you see, if you were to apply this transformation to a cube, so you got to start with something that has positive 3-dimensional volume. If you apply this transformation to that cube, what happens is that it just squishes the z coordinates. Right, so I'll just draw it like this. You start like this, just squishes this way. You still end up with something, but what you end up with is 2-dimensional, has 0 3-dimensional volume. So you need to compute the volumes with respect to the correct dimension. And the dimension that you should always look into is the dimension of the ambient space. Okay? This has 0 dimension. I'll do one more perhaps here. This one, again, it's a diagonal. This too is 0, this determinant. This time, in fact, you start with a 3-dimensional object that has 3-dimensional volume. It squishes it to this edge. Okay, it's a line. It is 1-dimensional. Consequently, it has 0 3-dimensional volume. Okay? When you're looking at determinants, you always need to consider the ambient dimension. So D is the dimension of the volume you should be computing to figure out determinants. There are always talk about sort of lower dimensional volumes in a higher dimensional ambient space, things like Hausdorff dimension and so on. And in fact, this box dimension I mentioned actually detects that as well, but we're not going to need that. For determinants, you just look at the dimension of the ambient space always. Okay? So these are the rules. And in fact, if you want to be super frugal with your memory, take this, 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 these two actually imply each other, but it's harder to see. I need to say a couple more words about how to sort of connect this to this case. Let me think. Okay. For now, I'm just going to state it as a rule. I'm not going to tell you why this should work. We're going to sort of try to make sense of it later. But another very important rule is that the determinant of a matrix is the same thing as the determinant of its transpose. Okay? This is not very easy to see geometrically. And of course, if you were to take this and take the transpose, you would get something like this. We'll make sense of this in a second. before that, I want to make sense of this plus or minus. So far, I didn't worry about the minus determinant situations. Here's how to make sense of negative determinants in a way that is compatible to what I've been telling you so far. Plus or minus in the determinant has to do with what is called orientation. Okay. Let's start with one dimensions, or one dimension. So if you had d equals 1, so you're just a line, and let's say you have a transformation A on the line, or that transforms the line, let's say. Okay, so this is A, here's 0, here's plus infinity, here's minus infinity. Okay. Okay, so A is a linear transformation from R to R. So it's a 1-by-1 matrix. Of course, it is nothing but multiplying by some number. Okay. That is invertible if and only if that number is non-zero. And if I'm looking at non-zero numbers, well, that is either plus or minus. Okay. If A were 2, the effect of this would be to expand the whole line by a factor of 2 without flipping. Okay? So maybe I can draw it like this. This small line segment turns into this, but it points to the same direction. If I had minus 3 as A, again, it would be a stretching, but it would also flip plus and minus infinity. Okay? So that's an example. Another example is A is minus 3. Okay. So this time, if I were to look at this small line segment, like so, say in this direction, and if I were to apply A to it, now it's going to be stretched by a factor of 3, and you're also flipping. Okay? Oop. So you're changing the orientation is what you would say. Okay? So at least in the one-dimensional case, determinant of a matrix, 1-by-1 matrix, is positive if and only if matrix preserves orientation. Determinant is negative if and only if it reverses orientation. In 2 dimensions too, the same thing works. If you think about a plane, well, there are 2 orientations. One is the clockwise orientation, and the other one is the counterclockwise orientation. So, and these two, again, there are 2 orientations, namely the clockwise orientation and the counterclockwise orientation. Maybe I can draw like this. Okay? And in fact, this counterclockwise is a standard one. For instance, if you were to think about this rotation matrix that I defined, the standard way to orient the plane would be to go this way. You would rotate this way, not this way. Because somehow, for those of you who know calculus, you want to sort of have your cross product vector to point out the plane. Okay? But again, it turns out the determinant of a 2 by 2 is positive if and only if it fixes either one of these orientations, and negative if and only if it reverses orientations. So here's what I mean. So, example, for instance, if I were to look at this, which is a permutation matrix, okay, interchange. If I start with counterclockwise, okay, meaning if I were to start with this shape, when I apply a to it, of course we know at this stage it just flips x's and y's, and so you're going to turn it into this. And so if you were to take this picture and turn it into this, the rotation is going to be the other way around this time. Okay? And the determinant of A is AD minus BC as usual, which is -1. Okay? So when I see this determinant equals -1, 1 tells me A preserves areas, minus tells me it flips orientation. Okay? It turns out, no matter what D is, any RD has exactly 2 orientations in the same way. I think I can still sort of justify it in 3 dimensions, but beyond 3 dimensions, I feel like you should just take my word for it. Let's do one more. Again, there are 2 orientations in 3 dimensions. I'll do it like this, in fact. Okay, and the best way, I think, to convince you of this, assuming that you haven't heard of the right-hand rule, is to show you this illusion, in a sense. So when I draw this picture, clearly it stands for something 3-dimensional, even though I draw something 2-dimensional. But in fact, there are exactly 2 ways in which you can interpret this as a 3-dimensional shape. Okay? One way to interpret this as a 3-dimensional shape is to say, oh, this is yz, and x is coming this way. And I'm sort of looking at the 3-dimensional shape from above. Another way to think of this as a 3-dimensional shape is to imagine it to be high up there, and you're sort of looking at it this way. Okay, so could be looking at it like this, sort of like a corner sticking out, or I could be sort of looking at it from above. Okay? So somehow these 2 perspectives correspond to, again, the 2 orientations of 3-dimensional space. If you're more prone to seeing this from above, so that x is coming this way, that is called the right-hand rule. Okay? Because you're sort of pointing your forefingers in the x direction, your palm in the y direction, and then when you sort of do this curl, you get the z direction. If you're more prone to thinking of x as an axis that goes away from you, that corresponds to the left-hand rule, which, again, you do the same thing. It's like you point your forefingers in the x direction, point your palm in the y direction, and this time when you curl, you get the z direction. Typically people use, in sciences, people use right-hand rule, but either one of them are valid. And the same thing again holds. If I were to look at a 3 by 3 matrix, its determinant is positive if and only if it fixes orientation, negative if it reverses orientation. Okay, so that's the meaning of plus and minus in the determinant. We have a couple more things to discuss. I want to talk about how to compute more complicated determinants, but we're pretty much done with all determinant matters. Like I said, we don't have class on Monday. We're going to be back on Tuesday. Thank you.